Okay, let's begin. Welcome again. And so you remember that we talked about this category actually a lot, right? So let's say C is some small category, then
Can you remind me what you call it something pre-sheaves?
yes,
Or pre-sheaves?
I'll tell. Yes. So we talked about this category. It's a topos. I said that I don't like it because it is not generalized enough. And also I said that I have three reasons, say. If you remember, I had the logical thing. And if you don't remember it, it's just not important for now. And I said that I have some geometrical reason that I don't like the guy, and some algebraic, right? And I said something about this guy, but not the other two. For the other two, I said that I need to read functors as some generalized spaces. Then I can explain what's wrong with this, right? So then we went to actually work with set to C opposite. So it doesn't matter really because C can be anything. So here I pretend to have C opposite. And then any functor here is called the presheaf on C, right? So there is some opposite thing there. And so we had this category of, say, category of, that's just another name of for functors, presheaves over C, which is equivalent to just functors from C opposite to set, right? That's just the name. So of course, it's also a topos because it's just the same thing. And so the main thing that we were talking about, I guess, for 2 sessions or even more, was reading any functor here as some sort of generalized space. And so here's the idea. So the idea, if you remember, was that I have the category C of some objects, right? And then I read objects here as simple objects in some informal sense, some simple spaces, some maps between them. And then I ask how to construct more complex things using these simple objects. One solution was just gluing them together. And the other was reading actually any functor from C opposite to set as a generalized space. And the idea is that, let's say that I have some sort of generalized space that's just kind of curvy. So think of these guys as kind of flat and this guy as some curvy sphere. And then I said that you can read any f as f of A is an object here, as all maps in quotation, some sort of maps in abstract sense from the symbol space A to this complex space, say Y, right? So I interpret it like this. And so in this sense, any functor can be interpreted, any functor like this can be interpreted as some space, and we understand the space via all the local maps, like this. Yes, yeah. So it changes, of course. Right? So this is just all the local data, and local means something here. And then if you combine all of them in one functor, then in some sense, this functor encodes some space. And then since there is no space really, so you can pretend that the functor is just encoding some space, right? And then we saw this thing that, okay, if I have functors as generalized spaces, then any simple space, any object here, say object, should be, any simple space should be also a generalized space. And then we had this Yoneda thing. So to any A, we assign Yoneda as some, say, object in set C opposite. So here is again the picture. Here is the picture. So I have C, I have set to C opposite, generalized spaces, simple spaces, and then to any simple space, I assigned Yoneda A, somehow a functor. And then we saw that actually this Yoneda functor maps this guy C inside set C opposite, and it embeds actually there. So then any simple space is actually a general space. And if you want to know the Yoneda A, maybe you forgot, so it should be a functor, and it simply reads B and computes the set B A. So anything below A somehow. So this is what we had. Also, we had something about the set to C opposite as Fico completion, but whatever. So now I can say something about the second problem, the geometric problem, right? Reading anything like generalized spaces, there is something that I don't like. To explain, first I have to provide two examples. So let's say that my C is fixed as opens of some topological spaces and the order, so this poset. And then let's say that I also fix some space, real topological space Y, and then set these two forms. So F index Y, say, so Fy, Gy, say, goes over C opposite to set. So that's example. And define Fy, so it should be a functor, right? Define it over U as what? As all, the set of all continuous functions from U to the fixed Y, and define, of course, then because it's a functor, so you have to also define it over, say, the inclusion UV, right? And this is just as we had before, restriction. And then define G of Y of U as, so all constant functions. And say G from U to 1, right? And again, Gy of U subset V is just restriction, right? Because restriction of constant function is constant, restriction of continuous is continuous. So these are two functors. With this new kind of interpretation that we have, we can interpret these two as two sorts of spaces, right? But the problem is that always we have space Y, right? Here and there, right? So you see, I have two different functors. Both of them are maps inside to some space Y, and Y is fixed. So then why I have different functors? Because I have different maps, right?
That's right, the functor is taking you to a second function.
Yes.
That's a single functor.
Yes.
Okay.
Right? The difference is between the maps.
Fine.
No. Y is a big Y, just one space. Right? So the point is that there are differences between maps. So I have to be actually more precise here to say that when you have a functor, the functor encodes two things, not just one. One, kind of curvy spaces, one type of maps, right, that you can choose as continuous, constant, I don't know, differentiable, whatever, right? There are 2 degrees of freedom, some space and some sort of maps, right? So now here I have the space Y and different sorts of maps, right? Like continuous functions and say constant functions, differentiable functions, and other functor, etc. So what's wrong then? Do you see what's wrong really? Of course not, right? So because it's just not obvious. Okay, so the idea is that, so these are 2 examples, and always we can read a functor as some sort of general space. That's good. Also, of course, it is good for a geometer, right? Because geometer likes to have simple spaces and somehow work with them to construct complex spaces. That's also fine. And also they are interested in different spaces and different types of maps. Therefore, they are interested in different functors. And of course, they don't work with all the possible functors sometimes, right? Maybe they are interested in some sort of Ys, some sort of maps. They restrict the category of set to the C opposite to some subcategories that they like, right? So that's fine. The problem is that almost always the type of maps that a geometer works with are local, right? They can be continuous, differentiable, whatever, right? But always they are local. In what sense? In the sense that the behavior of the function is actually determined by the local data, by the restrictions. So the example helps. So this type continuous map is a local thing, because checking continuity is a local thing, right? You want to check something is local, it's continuous at some point, you go locally there. But this guy is not, right? Being constant is a global thing. It's not a local thing, right? Why? Because I can have, say, 2 opens, this joint, this is the whole space that I have. The function here is 0, here is 1. Locally, of course, always it is constant, but globally it's not. Being differentiable is local, because you go around something. Being integrable is global, right? Because something can be integrable, say I have R, and I partition it in like this, and in each of these guys, you may have your integral, but the whole integral maybe is infinite, right? Etc. So there are some global notions and local notions, and always local is the thing that the geometer likes, right? So if I want to formalize generalized spaces such that a geometer likes it, it should not be just a functor. It should be a functor that encodes local maps, not maps.
Your picture of a functor,
Yes?
a general functor, what are these maps?
We don't know, right? So it is just a functor, and the functor says that it seems there is a space there, there is some sort of maps there, right? And then we encode those maps.
You get maps arising from the definition of functor.
No, that's something else. So the whole point is this. That they shouldn't. In general, they shouldn't, right? The whole point is that it is just a functor. So for any A, f of A is a set. It's just a set. It can be anything, right? Set of numbers, set of. Yes. So the point is maps is in quotation, right? So my point is that f of A is a set. You can read any element of the set informally as some sort of map from A to some space, right? That is just my reading of it, which axiomatizes kind of this situation, right? In some situations, you actually map the object U to maps, really. Sometimes you don't, right? But you can read them as if you are doing this, right? Okay, so the whole story is then my task is this, that maybe I have to restrict all functors somehow to some functors, some of these, that I can say uh, that they are encoding that they are encoding local maps, local type of maps, right? So what do I mean by that? I mean, here, maybe you have some property for this functor or the functors like this, like differentiable functions, whatever, which is not true for the constant one. And maybe I have to axiomatize that as well, right? I have functor with that property, and then I say that, okay, now I'm just interested in local maps, right? So what kind of condition is true here, which is not true here? And of course, it is somehow related to being local, right? Now do you see it? So being local is what? Is that if I have some f over u, actually I can determine it by restrictions on some, neighborhoods. If the whole neighborhood covers the whole space, that's some part of it at least, right? Mhm. And of course, this is not true here, right? Is it true? Of course it is, because all the time the function is determined by the restrictions. If it is, so then we need something else, right? Okay, let me write. So first, the first thing which is true always here is this, that if I have, say, f, it's just a motivation. Yeah. Then after the motivation, I will have the definition. So let's say, so my task here is that find something about locality which is true here but false here. So one thing that's true in both of them actually is this, that if I have, say, two functions from u to y, such that, and also u is union of some ui's. Thanks. Then if restrict f to ui equals to restriction of ui for any I, then I have f equals to g, right? So simply I'm saying that the function is determined by the local restriction, right? And it is true actually in both of them. It is something related to being a function, actually, not being local, right? If I have two functions and cover u by things, then if it is equal everywhere, then it's really.
Structurally functions talk about covering.
Uh, yes, exactly. But we are just here, so for now, yes. So at least whenever I have this open, then I can. But abstractly for any C, no. But let's say that I have just O of X. Then the second thing, which is really true here but not here, is kind of this. Let's say that I have a sequence of functions all continuous for any I, and of course I have the cover. Then if the sequence is kind of compatible, then there exists a unique f, or actually one f at least, from u to y, such that for any I, f restricted to ui is fi. What I'm saying, I'm saying something like this, that let's say I have U, and then this is not necessarily a partition, but whatever. So this is just U1, U2, U3. I'm saying, okay, that's bad. Right. So let's say that this is U1, this is U2, this is U3. So there are some things. That's just worse. Huh? What's wrong with this? U1, U2, U3, and the union of all the three is U, right? So what I'm saying is that if I have a function over U1, another function over U2, another function over U3, then I can glue them to one function. Of course, not necessarily I have to have a compatible family, meaning that on the intersection, the two functions should be equal on any intersection. And if I have that, then I can glue them together and construct a function, right? That's true. And since I have the first guy, the function is just uniquely determined by the local data. This function is actually unique. It's just one function. Because if I have another one, then they are just equal locally, therefore they are equal. That condition is true for the first and not for the second. Of course, always I can just glue the functions together. But the problem is this. If I glue continuous functions together, then I get a continuous function. If I glue constant functions together, I don't get a constant function necessarily, like this, right? So what I'm saying is this. So if you have the local data, you can construct the global data uniquely if everything is compatible. And that really means that your data is local. Because you can just glue them together and then you get the whole big picture, right? If you have something global, then knowing locally is not enough to construct the global thing. Maybe you can construct a function, but then it is not integrable, it is not, the condition that you have. Right? The function, the continuous function is determined really based on the compatible local families. The constant function is not. So that's the difference. And it captures locality, and I can axiomatize it, but of course, for now, for this guy, because you know what. So definition. No? A pre-sheaf F over this guy, pre-sheaf this, is called a sheaf if you have the following property. If for any open U and any, it's of course open, an open U, and any cover union of some UIs, we have the following. The following is that for any compatible family, family what? Family XI. I will explain what it is. There exists a unique X. So these guys are in FUI. This guy is in FU, such that row of UI. Say, I don't know what was the name, but I will explain again, of X, I guess U, U, Y should be. Huh? No, that's it. What is a compatible family? So the definition of this guy. This is compatible if for any I and J in I, X, Xi, so rho U I U I intersection U J of X I equals to rho U J U J X J. Thank you very much. What the hell is this? So let me remind you, right? So first I have a functor, right? So what's a functor? A functor means that for any u, I have some f of u as a set, but it is a functor. So if I have u subset of v, then there is a map from f of v to f of u because it is just opposite. And I call this guy, say, ub, right? And so always I have a function. Yes. So in yes, the smaller one.
Correct. There, but
Really? Ah, yes, 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 yes. You're right. J U I, right? Yes. So that's my notation. That's ugly, right? Always you have rho u v. The intuition is that you have a function, right, over v, and you restrict it to u, like we had there. So sometimes they just write restriction. So then this function is just restriction to v, right? Of course, there is no restriction because there's no function really here. These are just elements, some sets. But this is just suggestive notation, and I'm trying to just avoid it for now because it would be confusing, right? But just restrict. That's it. Come intuitively. So then what I'm saying here is this. So you have some u. You have your u. Yes. So you have this, say, u1, u2, u3, and the whole thing is u. The union is u. So then xi is in fui. Intuitively, xi is just a map over ui, but it is just simply an element in fui, right? So I have something here.
F of U is the set
Yes,
of this.
just a set.
How different?
It doesn't. It's not really a map. It's just an element. But to understand it, I'm just pretending that it is a map, but it's not really. So technically, it is just an element in f of u1, right? Okay, okay. Let's go with this. So I have x1 here as a map in fu1, x2 here, x3 there, right? Just three elements. So I say that the family is compatible when you have a map to go to the smaller things, right? When you have f of u, then you can go to the smaller things. So then you can go from u1 to the intersection u1, u2, right? There is a map mapping x1 to the guy, and there is also a map mapping x2 to the guy, right? Right? Why? Because I have this. Where are you? So, right, if I have something like this, if I have something like this, right, then I know that there is a map from FU to FU intersection U1, U2. There is also a map from U2 to intersection U1, simply because this is a subset of that, right? From two things, you can go to the intersection. So then if I have x1 here,
Following this map,
Just a function. What? No. No. Formally, it's just a function. It's a function row that you have it because you have a function, right? You have just a function and in a good way, right? So FU to FU is just identity. If you go from FU to FV to FW, then the composition is just the whole thing, right? What's the functor?
That's what I was gonna ask.
Yes. Let's again go here. So when I say that I have a functor to set, I mean f of u is a set, any set. And for the maps, when u is a subset of v, I should have a map, a function in set from f of v to f of u, something, right? Some function. But that function has some properties because it's a functor, right? So it should map identity to identity and respects the composition, right?
Okay.
Right? So therefore, I have just some sets for any u, and if u is less than v, then I have a map from f of v to f of u, and these maps are good. If I combine two of them, then you have. We don't know, right? It depends on f. It's just a function.
The particular function, the translation of
Yes, yes.
but you don't know what kind of thing that translates.
No, but they have just some properties of it. Like row u is identity, right? Right. So the only information that I have is that f of these guys are sets, and if I have some canonical maps, say when I go to something bigger to the smaller, then I have a map, really. So then what I'm saying is that if you have some x1 in f of fu1, right? You call this guy, the family, compatible when they are equal on the intersections. But how to have it? So the point is that there is a map, the row map here, right? So you can go from x1 to the intersection, right?
Here, x1 is a member of FU.
Yes. So the guy is here. You have a function. You apply it, then you have something here. That something here is this. Then you go from x2 with the map to the same set. The guy is here, right? Then I say that it is compatible when they are equal for any choice of any two, u1 and u2.
When the image.
Yes. Right? So that's just the abstract thing. But intuitively, I'm saying that if you read, that helps. If you read x1 as element here, actually as a function over u1, then that is the restriction to the intersection intuitively. Then I'm saying that two things, if the restrictions over the intersections are the same, then they are compatible family. Right? And then the sheaf condition simply says that if you have a compatible family, then actually there exists unique x in f of u, f of the whole thing, right?
But why should it be possible to read a member f of u as a function on u? Is that a consequence of this locality condition itself?
No. Informally, I can do whatever I like, right? As long as everything is consistent, because that's intuition. But formally, Yoneda lemma helps to read anything as some sort of generalized map, really. But that does not help, really. So what is the sheaf condition? The sheaf condition says that if I have some x's in a compatible way, there is unique x in the union such that if you go from now, this time f of u to f of any ui from x, then I get xi, right? Simply, I'm saying that I have some function over the whole thing that if I restrict to any ui, it becomes xi.
Sorry, can you write that with one?
Which one?
Then we just realized.
Yes, that's it. For any compatible family, there exists a unique x in f of u such that you have this for any alpha. Okay? It would be easier if I am allowed actually to write this like, right? That's better. If here I'm allowed to write x on. That's a bit misleading, but
That's
still,
xi.
yeah, that's x. Okay, so that's my definition of a sheaf. Intuitively, any pre-sheaf captures some space and some maps to that. Sheaf captures some space and some sort of local maps to the space. So if you are interested in not just some sort of maps, but maps that are also local in some sense, then you have to work with sheaves.
But should we be able to tell what the maps are in this? Well, I guess I asked this already. You said the functor is like sort of
Yes, but if you want really something formal, then the maps are just natural transformations from Yoneda to F. But
okay, can you say that again? So what are the maps?
you can interpret maps, but I don't want to. That's the point.
It's just you said it was defined with them.
Yes. So you can, it can be, okay. So if you really insist, then I can say this. If I have, say in this setting, right? If I have x in f of u, I'm just saying that you can read x as a map, but you cannot, right? So if you want really to read x as a map, then it is possible. X is kind of equivalent in some way via Yoneda lemma to a natural transformation, say assigned to x, from the Yoneda of u to f. So you can read the f really as some object instead to the C opposite. You work with the copy of u, the Yoneda u in the set to the C opposite. And to any x, uniquely, you can assign some alpha as a map from this Yoneda of u to really f.
And then this is the map that is local.
Yes. Okay. So that's kind of too abstract, I know, but that's what it is. So, okay. Any questions?
Is there a definition of this in a more top not in this language of categories?
You can just actually, I did actually open up the thing, right? So you have to open up what you mean by functor. Sometimes people do that, right? They say that we have this data. What is the data? Assignment to any open U, a set. To any pair U subset of V, a function. Such that rho UU is identity, rho UV, rho blah, blah, right? Then this data is called the pre-sheaf. We call the data a pre-sheaf, a sheaf, when for any cover like this of blah blah, if you have the elements in the sets, right, which is compatible in this sense, and this is, you can say,
Is this presentation still using the
no. You can see there is no Yoneda lemma. There is no really maps, right? Everything is just some element here, and there is some canonical function from f of say u to f of the intersection. Go over that function, you get two things in one set. They should be equal, right? Everything is just pure set theoretical. That map thing is my interpretation, but you can just forget it. Formally, you can just write it down. I did. Right? That's messy, but it is just formal.
Say something, talk directly about that. You motivated this by talking about maps.
Yes.
Locally occupied
Yeah.
as something topology.
Yeah.
But these, but I don't know anything about topology. But now you're not saying anything about maps at all, even in your topological paper.
Yes, I see your point. But the point is that you know, I have some functors that are really functions in your interpretation, just really geometric, right? But then I have also some other functors, just functors from C to some set. My point is that first, you can pretend that they are capturing some sort of maps. That's my pretension. Two, even here, there is a difference between local and non-local. You can axiomatize it somehow via this property. And then if you add this property to a functor, again, a very general functor, you can pretend that the maps that you can pretend they are there, they are local, right? It is some sort of generalized notion of map, generalized notion of locality. So I'm not just trying to capture this, right? It is also possible to do that, but you know. So about the definition, everything is clear. No, this is my next step. Exactly. Right? But about this definition, is it clear? Right? Okay. So, and is it clear that it captures that notion of locality? Right? Okay. So, next is this. Let's say that I want to have this notion of sheaf, not just on this C, but on any C. I need something. Exactly. I need some extra structure. Just being a category is not enough. Because being a category is some sort of order here that I'm using. Yes. Like here, that I have a functor, then I have restriction. But I also have this guy, the union, the cover. So you cover something with something else, some family of something else. And then I need this intersection because I have two things, then I restrict to say that they are equal. Right? I need these two structures in some general sense. First, actually, you don't need this. You can simplify it. Right? You want to say that two things are equal, so and say that I don't have any intersection, right? In my hand. I cannot talk about intersections. Okay, whatever. I say that for any V, which is subset of both of them, then the restriction are the same, right? So I can say it without having intersection. So therefore, the main problem is this guy. Some notion of covering, right? I need. If I have some good notion of covering on any category as extra structure, then maybe I can say these things and I can define sheaves as opposed to pre-sheaves, and then that's good, right? Because then I have locality not just over this category, over any category that I like. So if I have some category of simple spaces in some sense, maybe I also have some sort of locality, some sort of covering between my simple spaces there. And then I can talk about being local in generalized settings, not just topological settings. Okay. More than so actually I need at least some sort of join.
Yeah, okay, so, but like covering would be just joins in process, right?
Yes, but I'm okay. That's true, but the point is that you need something a bit more than having just joins. You need some sort of distributivity that we will see later. So, but if you have some sort of distributive lattice, say, or distributive complete lattice. So we can say yes. So there is nothing really topological here, because I have just union, any union, finite union maybe, and just intersection. And but you cannot see, but it is important that the intersection distributes over union in some sense. So let me then go for some arbitrary category. Let's say that I have C, a category, small category, whatever it is, and then so C, and then I want to add more structure as some sort of cover. Right? So what should be cover? Really, what is a cover? What is the generalized notion of union? Really, you can be really specific to make it union, or be a bit relaxed to see that covering in the sense of union has what kind of property to axiomatize. Right. At least you have a cone, of course, yes. Exactly. So what is first something like this, right? So because remember here it is a poset, so maps don't matter, but we have maps there, so we have to also handle maps. Okay, so if I write it map like, then this guy is something like this, right? So you have U here, UIs are subsets of this, and you have a family of them, right? Let's say U1, and this is just a map, U2, say UN, right? You have a code, one object, some objects above it, and some maps. Maps don't matter here, but maybe it matters in C, right? You have just a cone. Of course, not all cones, like here, not all cones are covering, right? Because the only thing that I'm saying here actually is that I have a sequence of subsets, but I'm not saying that the union is U, right? The union can be smaller. So in general category, I have to specify some cones like this, right? Technically some co-cones actually, that right, that are covering in some sense. That these guys via these maps cover you in some sense, right? So how to do that? So the point is, please. Thanks. It's weird. Maybe because okay, that's good. Thanks. So what does it mean? Right? What do you expect from a cover? Who knows, right? You can be a bad guy and say that, okay, let's say that C has a co-limit and then that's a co-limit cone, but that's cheating, right? It is just really the union in categorical sense. It's just too specific. Maybe the notion of covering is more generalized, right? That one is one of them, right? I don't want to construct one covering. I want to construct a notion of covering, and that guy is one of them. The co-limit is one of them, but maybe there are more. Okay, so here, do you have any idea? What should be the axiom? For now, for any U, I have some things over that. I can say that these are coverings from now on. Yes.
Isn't it the one that economic is disjoint union?
Just union.
And not the economic is disjoint union,
The coproduct is. Not always in set it is.
Yeah.
But here the coproduct is real union. It depends.
Take like the definition of polemic, but realize the recurrence property, then there is just like one of
That's not bad, but even better, I wouldn't say. I want just to pick whatever I like as cover with one axiom to say that it is just a good reasonable cover, right? And this is the axiom. if that's not obvious, so you have for some reasons you have to work with it to see. But if you think about this, then you see that okay, this is my U, this is my say covering, right? Whatever, let's say 2, 3, whatever. Right, okay. Some U's, right? I'm covering this guy. So of course, all of them are subsets, then I have the cone, but it is covering in the following sense. It covers, meaning that if I have some V, so let's write like this. So I have U, I have U. Let's say U1, U2, U3, why not? Just these three. And these three cover the guy in the following sense, that if I have some V less than U, some V here, so with another color maybe. So if I have, that's really bad, but sorry. So if I have some V, right, as a subset of U, then if it is a cover, then I also cover V. If you cover the whole thing, you cover V. Meaning that there are some parts, right? So that my thing is very bad, sorry. So just the easy one is this. So this is U, this is say U1, U2, right? I'm covering U. Then if I have some V, there are also two parts. One part for U1, intersection V, say. The other U2 intersection V, that covers V, right? What I'm saying is that if these three cover U, then for any V less than U, there is a cover, say, V1, V2, V3, such that each V1 is a subset of U1, V2 is a subset of V2, U2 is a subset of U2. If you cover something, then restriction to something smaller, you can't restrict these three guys to something else that covers, right? That's a very reasonable thing to say, because cover means cover everything less, right? That is my axiom that I want to put there. So then, what is a coverage? Definition.
Family covers you just if all is true for every family of sets. And then it'll also cover any subset.
Yes, it can be one of the coverings. Yes. Yeah. The point is that it is just very relaxed definition. So you can come up, and I will, with many nonsensical examples. So, but definition, a coverage over C, a coverage J, that's the usual notation for it. A coverage J over C is a function, say, assigning to any object A, so A is my U here, A of C, a set of families of maps into A satisfying the following condition. So first, what the hell is this? So what I'm saying is this: J is a map, is a very weird function that let's be here. So J is a function. It reads some object A, and it says here all the covering families, right? All the covering families, it actually specified. So for instance, here, J of any U is actually all the family of UIs such that the union of UI is U, right? So any element in J of A is a covering family. What is the covering family? I'm just specifying, right? Everything here is called the covering family, such that you have the following property, and the following property is this. It is the better version, more morph-like version of this. So for any A, and for any covering family, covering family what? Fi from AI to A, right? So for any A, for any covering families, now I have to also specify the maps. Let's say A2, F2, etc. For any this, for any map G from B to A, this is my new version of B is less than A, right? A subset. For any B, there exists covering family, say GI, GJ over B. So there is a covering here. Let's say B1, B2, whatever. Exactly. It could be another set. And so G1, G2, such that the only condition that I have is this. G composed with any GI, so GGI, is factored through one of Fi's. Meaning, maybe meaning what? Meaning that I have, so just specify one of the things. So maybe I have A, I have B, I have one of the BJs, GJ. What I'm saying is that there is some AI, Fi, and a map here that this guy commutes, right? You can factor it. So intuitively, what I'm saying is this, that for any, you have a cover, for any covering family, for any map, let's say B somehow is less than A, you can also cover B with something, and everything here is somehow less than one of these A's. You know, it is possible that some of the A's are just not used, right? Because the sets are not the same, right? Or you use some A twice, more, I don't care. The whole point is that any B, any this map, anything like this is just factored via one of the F's. It is, you cover via one of the A's. That's it, right? So simply I'm saying that this map factors through this, meaning that there is something that the composition is. No, that's the point.
So there's I and J.
Yes. For any J, the composition factors through one I. I don't care. It's not the same. Yes, yeah, you kind of right.
Sorry, can you read that just again, but you snap it to the side?
For any A, for any covering family like this from AI to A, for any G from B to A,
G is function.
G is a map in the category C. We are in some category C, right? So for any map, there exists a covering family over B.
GJ.
Is a covering family.
What's
Where's the bracket? J. This is J.
GJJ.
Gj index J. It's a family in J. Yes, over B, such that for any J, the composition GJ, GGJ, GGJ, GGJ factor is factored through or factored through one of the FIs. Okay?
And this is meant to be the same as the thing you were saying about sections of subsets.
Yes. It is the generalized more morphed version, a bit relaxed version of that, right? So any map J like this, any specification of the cocoons with this stability property kind of, then you can call it a coverage. And any element in J of A is just a covering family of A.
Again, the factoring is stating the existence of
Yes.
some top arrow. Of that.
Exactly, such that the composition, the guy is commutative.
So if your category has pullbacks, you can close any system into a coverage just by adding.
Yes.
In that case, the family of all possible families would be like the biggest coverage. And you also have the other trivial case, like the empty family.
Even you don't need the pullback. So we come back to that. Yes. So there are two obvious families of coverage. So some examples. The first and the most obvious example of the coverage is this, right? It is just
Right, there's no condition on it.
yes, no. So it's just a set index, whatever. So example number one. Of course, if your C is the O of X and this guy, then you can simply define J of U as I said, all the UIs such that the union of UIs is U, right? So maybe I won't do this anymore, but for at least once. But the whole point is that if I have U and then I have UI as a subset, right? Then I call it cover when the union is U. Then I have to check that condition to make sure that it is really coverage, right? The condition is, please move me. The condition is this. So for any map, meaning V, right? There should be a cover here such that each element is less than one element here. So of course use this UI intersection V, right? The intersections, of course, cover V. Each of these guys is less than one of the guys there. That's fine, right? Because there is no really maps. The being factored simply means that this composition is factored like this, then it means that this should be less than some of the guys. Yeah. This is just obvious. Even over any poset, you can, so let's say that I have C is just, say, a bounded distributive lattice. Then you can say that element A is covered via some AIs, A1, A2, etc. But this is just finite this time, not anything. Then the union of AIs is A. The join of AIs is A. So I have to check for this definition that condition holds, and then it is a coverage. So what is the condition? The same as here, right? So you have A, you have AIs, you have one morph here, meaning that you have some B. So I have to put something here. So I put B conjunction AI, right? Since it is distributive, B, so the union of these, the join of these guys is actually B union of AIs, which is B A, and since B is less than, so to make sure that it covers, I use distributivity. Because here when I say finite, I mean also empty. So, but doesn't matter. So yes, but then these guys should be not any finite, just non-empty finite. Because the join of empty must be just zero, so I need it, but it doesn't matter. So this is actually the finite version of the one above, that you have just finite things simply because the join of finite things is meaningful. So that's it.
Sorry, the definition maps into A.
Some morphisms to A, yes. A family of morphisms to A.
Objective?
No, just maps to A. So here you have just at most one morphism if you have something less than the other thing. So yes, no, into means that you go from something to the yes. So it specifies just the target, so nothing else. So example 3. What should I say? Oh, there are many coverages. So since I am here, okay. Since I'm just in the posets, maybe 2 other poset thing. So let's say that I have a poset this time, anything. But say finite, just to simplify things. And I say a family of AIs, which means just less than A, right? AJ, etc. A, A1, A2, etc. So this family is covering if the set of AIs, all for all i's, the whole set here, is the set of all minimal elements less than A, right? So something covers A if those things are first, all of them are minimal elements less than A, and you have all of them, not just some, right? Kinda, it is really a notion of covering like this. So if my P is just 3, something like this, say, right? Then read it backward. So this is greater than that. So when you go up, it is less, right? Then this is my A, say. So what is the cover? All the minimal elements, but these 3 above A, right? So this guy. Somehow it covers really. Because wherever you go, you hit the bar, right? In this sense, it covers. So is it really covering? I have to check this condition, right? Let's see. So the point is that I have A, the cover, and I have B, and I have to come up with a cover over B such that blah, blah, but there is just one cover over B, the cover of all minimal elements. So I have to check that if I have a minimal element here, it is less than a minimal element there. A minimal element less than B is, of course, the minimal element also less than A. So it is here. Oh, right? So in this sense, what I'm saying is that if A is here, if B is here, all the minimal elements above B is a subset of the minimal elements above A. And therefore, I have that condition. Yeah. Okay. Right? Yes. Yes, that's another cover. That doesn't work really because you have also you need that guy, but you can change it a bit to say that so okay, so you can change the cover to this. So that's another cover. To say that You have this bar, right? And whatever is above it. That's also important, I guess, to support the closure thing. But then it is a cover. It's another cover. Right? No. I'm introducing one specific cover. I'm saying that a covering family in my coverage now is just the set of all minimal elements above A. This is just one specific cover that I'm introducing. And you are introducing another one. No, if I'm only, okay, so I have to define what I mean by coverage, what I mean by this. The family is in J of A if, like this is just the definition. Okay, what do you mean by identity?
You have exactly one function which maps A to itself.
It should be mapping A to some family, so you mean mapping to it to identity, say? Yes, that's another. I come back to it. Oh, but maybe some concrete ones. Now, and then, okay, another post that you will see later, but maybe another one is this. So let's say that my C is set. That cannot be actually true because C should be small, but let's just forget smallness for now. You can solve this property by just restricting to some cardinal and some subsets, whatever. And also, please move me. So let's say C is a set. And then here is the cover. So as Neil said, so if you have, it is similar to that. So for any object A, the covering family is now, there's no branch, just one map, right? And that map is the bijection. So what I mean is this, J of A is the family, is the set of the families with one element, all the bijections from B to A. Huh?
Like same example as the suggested.
Also isomorphism. Yes, and also in set specific, but
In general, if your coverage to be like robust under isomorphism, but like isomorphic focus.
no.
Sorry, so by optimizing awesome, so I was suggesting having a single cover.
Kinda, yes. Just identity, as you said.
And you're having all these possible things,
Yes.
which is, so what did isomorph do? Are you saying everything in this, what is the isomorphism?
Is it important really?
Okay, is the isomorphism important?
Okay. The reason that I changed your definition to this is not that I need really isomorphisms to be there or being closed under isomorphism. It is just I don't like just one identity. That's it. So it's a matter of taste, so nothing else. Another one could be really, I guess. No, it doesn't matter. So you can also define it like this. Just one map, the identity map from A to A, nothing else. So A covers itself and nothing else, right? Or any up to changing of the names you cover. So these are coverages. So this is a cover. You have to check this, right? So let's check this. I have A, I have identity, I have some map B. I need a cover here. The cover is identity B, because by definition, always cover is this. So then this guy must be factor to this, and it does. Of course, identity is a coverage. So you can do the same here, right? Up to changing some name, etc. Another one. Again, C the set, but then I have this. Again, one map, but this time it is rejection. Rejection is covering, right? You are covering the guy, really. So you have to check this condition. Let's check it. So I have A, I have B, that is surjective, some G from some C, some G, and I need some surjection here such that I have the factorization, right? So the best thing to check here is just to pull back and check what whether it works or not. So the pullback here is this. So let's say the D and the functions. So D by definition is just the pairs of CB such that the G of C is, so let's say that it is pi or F, I don't know what F of B. And this map is just projection to the first one, right? So of course it commutes. Here I have all the pairs, here and here, such that these two are equal. And here I have P1, here I have P0, right? Projection to this. So the main thing is that if F is surjective, this P0 must be surjective. And P0 is surjective, right? P0 is surjective simply means that for any C here, I have to come up with some B such that I have this, right? Okay, so I have C, I compute G of C. G of C is F of something simply because F is surjective, therefore it is surjective. So what I'm saying simply is that in set, the pullback of a surjection is a surjection. I'm using that. And prove that, I'm proving that, I'm using it. Okay, another one. These two, I won't prove it, but they are easy. So the similar to these guys, but with fans, right? So the first would be, I say that this family of some functions. So I have some functions over A, not necessarily finite or anything, and then I call it cover when the induced map, right? Because I have some maps, then from the disjoint union, I have a map, right? This guy, this is a bijection. Another one, this is a surjection. So the difference is this. So if this guy is a surjection, simply I'm saying that the image of F's cover A. In the other one, when I say it's a bijection, I'm simply saying that F maps B to some part, B2 to the other part, disjoint. I'm just, partition A into the copies of B1, B2 via the F's, right? Either I cover really with this, with intersection or not. These are two covers, we can check the condition.
Just demand this subjection, it will still be like a disjoint part, no?
No, because the F's can map two things to one thing. And what else? So another, I'm not sure if it is important, but let's keep the definition. Another one. So, huh? In also it's a cover. It's counterintuitive, but it's a cover. Simply because you can do the same trick like this, and the pullback of injection is injection. So, but it's not intuitively a cover, but whatever. It is really a cover in our definition. So you can see that you have different covers over one category because, in different ways you have your union. So anyway, some general examples maybe help. So C, let's say C is just a category, whatever it is, right? And some general coverages. There are two obvious coverages, like you mentioned, right? One is the trivial coverage. And it is just very trivial. J of any A is empty. No family is covering. You have one A, nothing covers A. There is nothing there. And of course, you have that condition for obvious reasons, right? Because it says that for any coverage, for any map, blah, blah, but there is no. So that's just ridiculous, but you have to. Something less ridiculous, maybe, another coverage, is J of A is all whatever identities, like the set thing, because we use just being identity, not anything set theoretically, right? So that the condition is there because of this identity G. Because I'm stupid, simply. So that's just one. But for the other one, I need all, yes, all ISOs, all ISOs. Why it is good? Simply because if I have one ISO and another map, whatever it is, right? Then I have to come up with something, some ISO here. Should be B2A. Thank you. Exactly. Right? So I have to come up with one ISO here. Let's work with identity. Why not? And then I have to come up with something to make it commutative. And I can, right? Because this is G. F something should be G, but F is isomorphism, right? So then I say, I don't know, F minus 1G. Right? Because F is isomorphism, so just change it, put it somewhere. That's easy. Okay, so it shows that this is really a coverage because that condition holds. The condition that says that if we have a covering family, if you have another map, you have to find the covering family here such that it factors.
Yeah,
And-
you've shown it as one map, or are you using some kind of transitivity of
No. So the point is that I have to come up with a cover here, and I choose being identity because it doesn't matter.
Okay, well, I'm just saying that's not the condition of the definition. We were saying it will follow because identity is a cover.
Yes, because identity is isomorphism. So then, in some sense, all the three are the same, but we will see in what sense. Now they are simply different. So, but they do the same thing somehow. There is another one that is kind of this is just the least one. There is the greatest one. Define JA as all possible families. All possible families like this from any AI to A. Anything. Whatever you like. Pick just a whole column, it's a cover. I don't need it, right? Yes. So let's prove that it is a cover. So I have to check that guy, right? So how to check it? I have A, I have B, I have G, something here, because it can be anything. So now I have to come up with something here such that it factors. Okay, just pick the ones that factor. So here use all the G's, right? So all the GIs, right? GJs with that definition, such that GGJ is factored through one of the AIs. I don't care, right? It can be anything. This is the whole point. Yeah? The only condition that I have is that I have to come up with a covering family, but now a covering family can be anything. So I can come up with some maps here, even empty, such that the only thing is that the composition factors. So just use all the ones that factor. Who cares, right? It's just trivially there. The other one, C is small, so I'm assuming the C is small, so everything is a set. What is the next one? That's also stupid, but kind of cute. So all possible families that are so the same, but all non-empty families. This is then not trivial to be the family. So so here I have all the families, including the empty family, right? But here I'm saying that choose any family as long as at least you have one map.
Well, family is the setup of the index by I.
Yes. And I is a non-empty. Yes, with non-empty I. At least you have one map in your family. This is not necessarily a coverage because you cannot check this condition. So you have to add one condition to your category. And the condition is that if you have two things, then there is one cone. Then you can check it. The other one, yes. So for any two maps to one thing, there is one thing there such that it is commutative. I'm not assuming that I have all the limits in C. If I have pullback, then it is there, yes. But I'm not assuming. C is just a category, not a category with limits. Yes. So another one. So this guy is a trivial coverage. It has a name. This does not have a name. I guess it is just the greatest coverage or something. This non-empty thing has a name. It's called atomic, the atomic coverage. And we also have another one that is very weird sometimes. How should we find that guy? This coverage. So I say I have A and a family, right? I call it a coverage in new coverage that I'm introducing if any map B from B to A factors through one of them. It is the generalized version of that minimal things, right? So in the post-it, if you remember, I had this minimal thing, right? Then I said that this is a cover, all the minimals above the guy, right? All the minimals simply means that if you have something like here, it is less than one of the others, right? You covered all possible, in the future situation. And here, this is the morphed version of that this covers this, meaning that it bars all possibilities. If I have any map B, it goes through one of them. It covers all possible expansions families. Right, so what? That's true also. So it has a name. It's called dense coverage. And it's always a coverage. Yes, that's the same dense. Then what? Maybe I have to be a bit over time to complete this game of introducing coverages. So there are two other. So these are just the general coverages that I wanted to say. Some specific ones. So there is one on topological spaces. So you say that you have a topological space, you have some i's, some continuous maps, and then it is a coverage simply when the union of f of i's is, sorry, so when these guys are, there are two of them which one I want. Okay, that's hard to explain. Then that's just not useful. Okay, whatever. Just forget about this because that's trivial. The other one is this. Let's say that I have z minus 0, and this is just a division. This is a poset, right? The opposite of it. It's not really a poset, it is a pre-order, but whatever, right? Z minus 0 division. So therefore, in this poset, 2 is bigger than 6, right? Because 2 divides 6. So then what is a cover? So if I have A, something less than A are all multiplies of A, right? So A, say B1, A, B, N. So this guy is called the cover when the sigma of ABI is A, right? I have negatives, so it is possible. Like what? Like I have 2, 6, minus 4. Huh? That's also a cover. Why? Because I have to check that guy. That guy says that if I have something here, less, meaning that it is CA, then I have to have a cover here. And what should be a cover? Of course, CAB1, CABN, and the addition of these guys of CA. So you can see that it is kind of the same as the topological space. I'm changing union to addition, and then there I use distributivity. Here also use distributivity, right? That multiplication distributes over addition. So this is another one. And I guess that's kind of all the coverages that I wanted to say something about. Okay, so next time I use this coverage as my notion of union, right? And then I can define so sometimes okay, so first, if you have a category and a coverage over it, the guy is called the site. This is the extra information that I needed. And then using the site, I define next time that when a pre-sheaf like this is called a sheaf with respect to J, sometimes it's called J sheaf or whatever. And then we work with the category of all sheaves. This is subcategory of all pre-sheaves. The objects are sheaves, but the maps are all possible maps. So there is no restriction on the maps. It's just a full subcategory. And then we show that this is actually a topos, and we like it. This is the thing that we didn't have because we didn't have the locality. So this is the geometric problem. But then I have to also explain that this also solves this J. The locality also solves the other two problems. The algebraic one that I didn't mention, and the logical one. So therefore, I have, if I add this locality, then I have everything that I like. This is the best possible topos ever. Thank you very much. Questions?
What was the logical problem?
The logical problem is that set to the C opposite, it has the intuitionistic logic always. There's no natural machine to make it classical. The point is that there is some J that I can add on any C, and then the sheaves, this category would be classical. Everything would be Boolean. And actually, I can say what is this J. The J is this dense covering.
Did you say site, S-I-T?
Yes, S-I-T-E.
Is the category of all sheaves one of those categories of sheaves?
Yes.
One of the three.
The trivial topology.
Yeah, the top bigger.
Yes. It doesn't matter really which one. All of them are the same. But the first, let's say. And it's easy to see because there is no covering. Covering is empty. When there is no covering, there is no condition. The sheaf condition is for any covering, blah, blah, blah. So there is nothing, then every pre-sheaf is a sheaf. So then it's for trivial pre-sheaf is this. So it's generalized version of pre-sheaves.
Then I was like regarding that you say these three above are like somewhat similar. So I feel that there is some kind of like robustness or stability in the definition. Like if you have some coverage, and if you like make also at all isomorphic copies, that it's like somewhat the same.
Yes.
And another thing is that if this particular family is covering,
Yes.
if you add something more into the family,
Yes.
it should cover.
Yes.
If
Yes.
you do this, the property is still satisfied. So
True.
you can also like make it maximum with respect to like this.
Exactly. So there is some sort of closure conditions, exactly, and closure. So you have to have some meter to to measure what kind of closure conditions you need. The closure conditions are the ones that does not change the sheaves, and so then adding those closure conditions, you have somehow the maximal version of the guy. Those things are called Grothendieck topologies. And then, therefore, these three are the same. Simply means that the Grothendieck topologies of all of them are the same. So
And both of the situations I mentioned are like of that sort. that
yes,
don't
adding
change.
isomorphisms, but there are many more things. So it's not just isomorphism, but yes. Sure. Yes.